So this is an integral from the Berkeley Math Tournament 2020, and Black Pen Red Pen has already made a video on this integral, and he solved it using Feynman integration. So I provided the link to that video in the description as well, so do check that out. Quite a brilliant video, and subscribe to him as well because he makes great math content, seriously great math content. I'm a huge fan. And subscribe to me as well because we're going to solve this using more basic principles of integration, because no doubt Feynman integration is quite exotic when you try it out on this integral, but I was interested in applying some of the basics to solving this integral that looks really tricky. So let's call this integral I, and let's write the reciprocal of the tangent as cotangent. So we have x times the cotangent of x, and we're integrating with respect to x from 0 to pi by 2. Now, one thing we can try here is integration by parts. So let's decide to integrate this cotangent function and differentiate this x here. So integrating by parts gives me x times, now the integral of the cotangent of x is the natural log of sine of x. And the limits of integration were 0 to pi by 2 minus the integrated function, and of course the limits are 0 to pi by 2, the integrated function being the natural log of sine x times the derivative of x, which is just 1, so let's just ignore that. Now let's take a look at what happens when we apply the limits here. So as x approaches pi by 2, this natural log of sine of x, now sine of x will approach 1, so this log term will approach 0, right? So that's sorted out. But what happens when x approaches 0? That seems to be a more difficult question to answer straight away. So let's study this limit. We're studying the limit as x approaches 0 of x times the natural log of sine x. And this is more like a 0 times infinity sort of situation. So let's write this as the limit as x approaches 0 of the natural log of sine of x divided by 1 by x. And now we can actually try L'Hopital's rule. So differentiating upstairs and downstairs, we get sine of x reciprocated, and you have its derivative upstairs, and that's the derivative of the numerator. And for the denominator, you have the negative of 1 by x squared. And of course, you're taking the limit, you're studying the limit as x approaches 0. So now I can just take this x squared and shift it right upstairs with the cosine term. So we have x squared, a negative sign out here, x squared times the cosine of x divided by the sine of x. And although this doesn't look that good on a first glance, just a bit of trickery here. We can write, because we have two x's, right? So let me take one x as the numerator of x by sine of x term, and let me just leave the other x term with the cosine of x. Now we have some familiar stuff. We know that the limit of sine of x as x, sine of x by x as x approaches 0 is 1, which implies that the limit of x by sine of x as x approaches 0 is also going to be 1. So this the first limit you're going to get is 1, and as x approaches 0, this is going to approach 0, and as x approaches 0, cosine of x is going to approach 1. So 1 times 0 all results in a grand 0. So coming back to our integral, we know that this entire term reduces to 0. And what about the second integral? Now this is something that you'll often see in introductory courses on complex analysis. And the result is negative pi by 2 times the natural log of 2. And I am going to prove this in just a few moments. So this is the result of the integration. And you have another negative sign out here, which all of this implies, since the two negatives cancel out, that the integral is pi by 2 times the natural log of 2. So that's great, our answer matches up. But now to actually prove what I stated, that the integral from 0 to pi by 2 of the natural log of sine x with respect to x equals negative pi by 2 times natural log of 2. And I said that this is something that you'll find in introductory courses on complex analysis, but I don't want to use any complex analysis here. I'm only going to use real techniques and the properties of the definite integral. So let's write the integral from 0 to pi by 2 of the natural log of the sine of x with respect to x as I1. Now, first up, use a phase shift. So if you're going from x to a pi by 2 minus x world using your phase shifting, then I1 is going to be equal to the integral from 0 to pi by 2 of the natural log of sine of pi by 2 minus x with respect to x. Now, we all know that this reduces to the cosine of x. So now you have the natural log of the cosine of x integrated with respect to x from 0 to pi by 2. So if this is the integral I1, then so is this, right? It was the integral from 0 to pi by 2 of the natural log of sine x with respect to x. So since both of them are I1s and we see that the variables and limits of integration are exactly the same, let's just add them up and see what happens. So we have twice of I1 being equal to the integral from 0 to pi by 2 of the natural log of sine x, and we can combine the two integrals, of course. So we can add up the natural log of sine x and the natural log of the cosine x, and we're integrating with respect to x. Now we can make use of some handy properties of the natural logarithm function. So replacing these two separate logarithms by one single logarithm means that you replace the addition by a multiplication of the two arguments. Now this expression for 2 times I1, it's also pretty familiar. If you look at the argument of, I'm talking about the argument of the natural logarithm, this term of sine x times cosine x is actually pretty familiar. We do remember, right, that twice the product of sine x and cosine x equals sine of 2x. So that means that this product is just 1/2 of sine of 2x. So 2 times I1 is the integral from 0 to pi by 2 of the natural log of 1/2 of sine of 2x. And we're integrating with respect to x once again, repeated. Anyway, sorry, I tend to speak everything as I write because I know my handwriting is atrocious. Anyway, so once again, we can make use of some handy properties of the natural logarithm function by noticing we can actually split up the 1 by 2 and the sine of 2x if we just split them up in terms of logarithms. So this is pretty useful as well because now we have a constant term to deal with as well that we can separate. We can separately write this as the integral from 0 to pi by 2 of the natural log of 1 by 2 with respect to x plus the integral from 0 to pi by 2 of the natural log of sine 2x with respect to x. Now this integral here will just reduce to the natural log of 1 by 2 times pi by 2. And what about the other integral on the right hand side? Well, let's study this separately as an integral I2. And yes, we started off with one integral and now to solve it we need 2 more. So yeah, good for us. Anyway, so the integral I2 is the integral from 0 to pi by 2 of the natural log of sine 2x. Now believe me, this is a lot. This has plenty of similarities with the integral we're looking for, that is I1. And let me make that clear in just a few moments. First of all, perform a substitution where we let 2x equal to t, which implies that dx equals half of dt, right? So I2 is actually going to be equal to half of, now the limits of integration as x approaches 0, t will approach 0, and as x approaches pi by 2, t will approach pi. So we're integrating from 0 to pi, the natural log of sine of t with respect to t. Now, it would have been really cool. It would have been really cool if we did not have a pi as the upper limit of integration. It should have been a pi by 2, right? So that would have made things so easy. However, we can do something like that. Consider the graph of y equals sine of x from 0 to pi, then this is the shape you're going to get, correct? So we see that the graph is symmetric about the line x equals pi by 2. And we know that the natural log of x is a one-to-one function, right? Meaning it's injective. So because the natural log is a one-to-one function, and we see that sine of x displays symmetry about the line x equals pi by 2, then instead of taking the entire interval, why not just take half the interval and double the result? So instead of integrating from 0 to pi, we're integrating from 0 to pi by 2 and just doubling the result. Now this cancels out the 2's outside, and we're left with I2 being equal to the integral from 0 to pi by 2 of the natural log of sine of t with respect to t, and this is exactly the same as I1. So I2 equals I1. So using this information, we have 2 times I1 equal to pi by 2 times the natural log of 1 by 2, which you can write as the natural log of 2 provided you add a negative sign out here, plus I1. So this implies that I1 equals the negative of pi by 2 times the natural log of 2. So I hope you enjoyed the video. Be sure to like and subscribe. Thank you. See you next time.